Hi, and welcome to 7-2 Day 2. Let's start with just a quick review on what we did in Day 1. Day 1, we had formulas that looked like this sort of structure. Now let's just clear this ink. So we first needed to identify both asymptotes. The y asymptote was whatever number was out there. So in this case, y equals 5. And we talked about how the x asymptote was our h right here, this idea that x equals 2, because the typical structure of x minus h plus k. However, we also did talk about in class how, technically speaking, we can set this entire denominator equal to 0 and solve for x and still get the exact same idea here. That's important because it's nice to recognize what can we never, ever, ever divide by. We can't ever divide by 0. So, intuitively, this also tracks. So for here, for example, I can set this equal to 0 and realize that I can't do anything, so that has to be my whole 0. Well, vertical asymptote is always the x equals. The y asymptote is the y, and in this case, whatever is left out there, so y equals -2. We should also remember that domain is with x's and range is with y's. So my domain would be everything except my vertical asymptote. So -infinity to 0, union 0 to infinity. And my range should be everything except the y value. So -infinity to -2, union -2 to infinity. Over here, I can set my denominator equal to 0. And realize that it's going to be, by adding 1 to both sides, we get x equals 1. And my horizontal's got to be y equals 5. So my domain, -infinity to 1, union 1 to infinity. And my range, -infinity to 5, union 5 to infinity. Over here, x plus 4 equal to 0. So we get x equals -4. I have nothing out here. Well, what's math nothing? That's 0. So I get y equals 0. So my domain, -infinity to -4, union -4 to infinity. And my range, -infinity to 0, union 0 to infinity. All that should more or less be revealed. So today we're going to look at a different equation structure, and that is y equals ax plus b all over cx plus d. Now, we still get both asymptotes. Vertical asymptote is still an x asymptote. The nice thing is, conceptually, it's the same thing. I can't divide by 0, so I can do cx plus d equals 0 and just solve for x, as I said right here. So the denominator equal to 0 and solve. The y asymptote is a little bit different. I don't have anything off the side anymore. The y asymptote is defined as a divided by c, where a and x are what have, a and c are what have x's. There's a big, long reason for this. What it comes down to is, as x gets really, 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 really big, the b and d sort of don't matter anymore. So let's take a look. Let's set our denominator equal to 0. -x minus 1 equals 0 and solve. So +1 plus 1. -x equals 1. Divide by -1. Divide by -1. We get x equals -1 for my first asymptote. Okay. The y asymptote, again, the numbers in front of the x. So I'm just going to divide them. So -3 over -1. So we get y equals 3. So my domain, again, everything except for the x asymptote, so -infinity to -1, union -1 to infinity. The range, everything but the y asymptote. So negative infinity to 3, union 3 to infinity. Now, of course, let's graph this so we can actually get some coordinates. So y equals, clear that stuff out. Alpha x to get a fraction, negative 3x plus 2 over negative x minus 1. Graph. Get some coordinates by second graph the table. I want 2 above and below the error, so let's start with negative 6, 4, and negative 2, 8. 8. And 2 below it, so 0, negative 2, and 4, 2. Same thing, let's set the denominator equal to 0. We get x equals negative 1 by minus 1 minus 1. And then we can divide, so we get y equals 2 over 1, or just y equals 2. So my domain, everything but negative 1, so negative infinity to negative 1, union negative 1 to infinity. My range, everything but 2, so negative infinity to 2, union 2 to infinity. And of course, we can graph it. Alpha x, 2x plus 3 over x plus 1. Second graph. This, we get a bunch of fractions, so just find one that's close and just round it. So like negative 2, 1, and like negative 6 and about 1.8. And 0, 3, and get something like this. Okay. Next, we have a story problem. A 3D printer builds up layers of materials to make three-dimensional models. Each deposited layer bonds to the layer below it. A company decides to make a small display of models of engine using a 3D printer. The printer costs $1,000. The material for each model costs $50. Estimate how many models for the average cost to fall to $90. Well, I'm going to make average cost be C. And I'm going to have X be number of models. So first and foremost, I'm going to have to create an equation. So let's think about this. If I make 0 models, I still spent $1,000 on the printer. So no matter what, I'm always paying that $1,000 for the printer. If I make 5 models, I still only paid $1,000 for the printer. The printer is independent of how many models I make. Now, each model costs $50. So if X is the number of models, I would represent that by 50 times X. And that process would tell me how many or how much I spent on the whole process. Well, by definition of average, you tend to have to divide by something. In this case, if I'm talking about average cost, I would divide by how many models I make. So my actual equation is going to be 50x plus 1,000 over x. And if I want the average cost to fall to $90, I'm going to put 90 in for my average cost, C. So I'm going to get 90 equals 50x plus 1,000 over x. And from here, I'm going to solve. The first step is I'm going to multiply both sides by x. So I get 90x equals 50x plus 1,000. I can subtract 50x from both sides to get 40x equals 1,000, and I can divide both sides by 40. So x would equal, I would need to make 25 models for the average cost to be $90. Or B, what happens to the average cost as more models are printed? Well, if I only made one model, 50 times 1 is 50, plus 1,000 would be 1,050. So yeah, if x equals 1, I spent 1,050 per one model, so my average cost would be 1,050. Well, if x was 2, 50 times 2 is 100, plus 1,000, I'd spend 1,100 divided by 2. My average cost would be 550. So I can already see that as I make more models, the price per model is going to decrease. Now, interestingly enough, it will settle at a specific value. It's not going to decrease forever down to negative values. Let's draw it again. Let's say I make 4 models. 4 times 50 is 200 plus 1,000 would be x equals 4 equals 1,200 divided by 4, that'd be about 300. So they're not even decreasing at like a similar rate. Well, I can use a concept we literally just talked about. Because if I were to graph this, we can all see that the C is kind of like the Y value. This average cost is kind of like the Y value. So functionally, if I can figure out my Y asymptote, I can figure out what value this would approach. Well, the Y asymptote would be 50 divided by 1. So the price approaches $50. Thank you for listening, and I hope you have a wonderful day.